Okay, Assalamualaikum semua. Right, so today's lecture is about spatial epidemiology. Okay, spatial epidemiology, and to be exact, is spatial epidemiology in communicable diseases. Right, spatial epidemiology in communicable diseases. Right. So next. Right. Okay, when we talk about spatial data, okay, spatial data, in this data, there is geo-reference. Okay, it means that you got a reference point, and then the reference point are basically geo-coded. Okay, geo-coded. It means that it has point locations. Okay, point locations. Right. So how do we do this? Usually we have two data columns. Okay, imagine you got data set, right? Data set. I mean, we are familiar with data set, columns and rows. So in georeference data, there are two columns which usually are represented by x and y coordinate. Okay, or let or long. Okay, x or y. Right. So those actually the minimum requirement for a spatial data. Okay, you got a column of x and column for y, column for longitude and column for latitude, right? So, and when you present your data in spatial data, you present as points. Number one, okay, it means that you can see for example, you see maps, right? And then you see points. For example, points of COVID-19 cases, right? Dot. Okay. And then you can also see lines. Okay. For example, roads, river. What else? Roads, river, electric lines. Okay, those are lines. Right? Those are lines. And then you see also spatial data that have polygons. Okay, polygons or area. For example, daerah. Okay, daerah in polygons. Okay, or state, Kelantan, Terengganu, Pahang. So you can see area. Okay, polygons. So those are basically polygons. Okay, so you got points, dot, lines, right, and also polygons. And you can also have volume. Okay, volume. For example, taburan hujan. Okay, rain fall, or apa ni, temperature distribution. So that are raster spatial data. Okay, spatial data in raster form. So you got vector and raster. So vector, you have points, lines, and polygons. In raster, you got the volume. Okay. So vector, and raster. Okay. So when you present spatial data, so you present as vector, and vector can have points, lines, and polygons, and you can have also raster, taburan hujan, for example, rainfall, temperature. Okay. And also triangular irregular network, or TIN. But I'm not familiar with TIN lah. I'm not familiar with TIN. I work mostly with vector, very rarely with raster, and almost never with TIN. So this is the basic data structure for GIS. So you got vector. Okay, so you got vector. And vector, you can see points, dot, and these boxes are basically polygons, and these are the lines. Okay, these are the lines. So you got polygons, you got lines, but you don't have points here. Okay, you don't have points here. And then you got raster. Okay, you got raster. Contohnya taburan hujan, and then the green taburan kata apa, hutan, things like that. Okay, and usually these are the remote sensing data lah, remote sensing data. And also a thin triangulated irregular network. Right. So basically that's the basic data structure for GIS. And now very common, you got attribute table. Okay, attribute table. It means that you got column for X and Y, and then you got attribute. Contoh, for example, you got special data for dengue, for example. So you got patients number 1, patient number 2, patient number 3, patient number 4. So these are 4 cases of dengue, for example, and then you know the locations for each of these 4 patients based on the X and the Y. And then in addition to that, you got column for the age, column for the sex, column for the income, and column for maybe tests of Aedes or dengue for that patient. So you got a combinations of spatial data with attribute table. Okay, basically kita panggil variables lah, kita biasa dengan variables lah. Okay, kita panggil variables. So again, spatial data have these variables. Some people call this or call variables as feature class. Okay, feature class, but feature class I think basically is variable lah. Okay, variable. Okay. So a collection of features of the same type, and dalam variable, to inside the variable you got attributes or values of variable. Okay, later we see this. Okay. So in terms of data collection and management, of course, when you want to do analysis with spatial data, then you need to capture the spatial data. You need to verify, for example, the locations of the coordinates. Okay, the coordinates, and also the structuring process. And very important that you need to specify the spatial reference frame. Okay, spatial reference frame. And this is usually provided by the coordinate reference system. Okay, coordinate reference system or CRS. Because why? Because Earth is not a perfect sphere. Sebab bumi ni dia bukan bulat sebenarnya, bukan bulat yang betul-betul bulat lah. Dia tidak bulat completely. It's not perfectly sphere. And in addition to that, dia ada tanah tinggi, for example, right? You got mountain, you got people living in mountain, on mountains and bangunan. So that's why bumi, Earth is round. It's not a perfect sphere, but it's round. But when you want to kita nak flatkan dia atas meja, it's very difficult. It's just like, okay, imagine you have a ball, okay, and then you want to cut the soccer ball too, and then you want to flat the soccer ball on the desk. Dia akan jadi hirot kan, hirot sana, hirot sini, hirot sana kan. So it is not perfect. So because of that, there's always issue with spatial reference frame, and scientists have devised quite a number of coordinate reference system to be able to project the map from the sphere to a flat that you can see on the table kan. Remember, if you look map dalam kertas yang apa ni, on a paper map, actually if you make them round, it will not be round macam bumi tu. Okay, so that's why you can see people manipulate maps. They can see, they can show that certain countries that actually is not big appears big on the map, and countries that are actually big appear small on the map, on the paper map. Okay, I think for example Antarctica and Africa. Antarctica looks big, okay, but actually it's not that big. Africa looks small, but actually Africa is huge actually in the real size. So people can manipulate maps based on the projections they are using. Okay, so projection they are using depends on the coordinate reference system or CRS. So the basic coordinate reference system is the geographical coordinate reference system. This is so the we call this as latitude and longitude. Okay, latitude and longitude. And then so latitude and longitude are basically the geographical coordinate system. It means that the coordinate reference system when Earth is sphere, bulat. Okay, and then when you need to flatten the Earth so that you can convert to paper map ataupun you see on the screen of your computer, flat kan, square tu, then you need to project the coordinate reference system. Okay, you need to project. Okay, so there are a number of ways to project the map. Okay, so one of the common projection include the universal transverse Mercator. Okay, UTM. Okay, bukan University Technology Malaysia. Okay, universal transverse Mercator, and it requires these mathematical expressions called ellipsoids. So basically map projections, okay, map projections try to portray the surface of the Earth, okay, on a flat piece of paper or computer screen. So imagine, it's very difficult. Okay, kita ada bola kan, kita gunting dia, kita nak flat dia kan, it's impossible. Dia akan ada tempat-tempat yang dia akan jadi herod. Okay, so because of that, scientists have come up with a number of coordinate reference system, and the coordinate reference system will define the coordinates and how we can project the map to a two-dimensional map that is correct and can be visualized on a flat piece of paper or on a computer screen. It's difficult. Okay, it's difficult. Imagine ada bola, potong-potong nak flatkan dia, it's very difficult. Okay, so coordinate reference system is very important actually. Okay, so there are two common types of coordinate reference system. First is the like I mentioned before, the global or spherical coordinate system. Okay, yang bulat tu, yang bulat. So this is where we always call this as a latitude longitude coordinate reference system. Okay, but more commonly known as the geographic coordinate system. Okay, geographic coordinate system. Okay, so geographic coordinate system represents Earth in a sphere mode, and we call the coordinate as latitude and longitude. Okay, and we have another one, the projected coordinate system. Okay, the projected coordinate system, for example, the universal transverse Mercator, Albus equal area, Robinson, and many other projected coordinate system. Okay, so the geographic coordinate system basically represent Earth in the sphere form, and the projected coordinate system is the way to flatten Earth so that you can visualize dalam computer, or you can visualize on a flat surface using a paper map and other things lah, on tablet ke, so and this, instead of we call this as latitude or longitude, we call this as Cartesian coordinate. Okay, Cartesian coordinate. And usually we call the latitude and longitude as x and y rather than lat or long. Okay, X and Y. Kalau coordinate reference system, kita panggil dia latitude dengan longitude. So the process of converting from coordinate reference system to projected coordinate system is called as map projections. Right. So because of that, that introduced some issues with spatial data, geocoding issues especially. Other issues, inaccurate and incomplete database. Okay, of course that happened everywhere. Confidentiality, because if you know the coordinates of some people, then you know it means that they are not confidential lah, kan? Privacy breach. So people are quite sensitive nowadays with confidentiality. So that's another thing that you have to look at. Okay, I mean you can't just go and say I want to geocode your coordinate, kan? Pergi dekat rumah, go to that person's house and geocode his house, kan? Because now people know exactly where he stays, right? Even they can send drone ke, you know, they can send bomb ke, whatever things lah, kan? So if I'm not mistaken lah, Google Map for example, I think they have some form of algorithm where they will somehow kata apa ni, pindahkan sikit kata what we call jitter the coordinate a bit. Okay, and then zip codes. Another issue, because for example in Malaysia, zip code or postcode represent the area of the post office service. Okay, not the residential area. In UK for example, the zip code represent the residential area, office area, or part of the university area. So it's really almost accurate lah. Okay, tapi in Malaysia for example in Pasir Mas, kan, postcode 17,000, it covers thousands of houses, kan? So it's so big, it's so much so that if you need to use zip code or postcode in Malaysia, it's very difficult. Okay, because it is not precise enough. Next is geocoding issue, kita dah bincang tadi, and locations of uncertainty. Okay, when it comes to analysis of spatial data, okay, when you have spatial data, you have the lat and the long, or the x and the y, and you know the the coordinate reference system, you know the projected coordinate reference system or geographic coordinate reference systems. So now you want to analyze your data, right? So how usually we analyze spatial data? Okay, number one, determine your analytic goals. Okay, for example, are you interested to evaluate differences in the rates observed from different geographical area? For example, if you think that okay, maybe some cancers are prone in certain areas, okay, for example areas near the power line, then you can geocode all patients with cancer, and also geocode some of normal participants. So you have two groups, right? Cancers and non-cancers, and then you geocode, and you see the distributions of patients and also the control, and see if and then you divide by the number of population in that area. So when you divide, you got the rates, right? The rate of cancer in Pasir Mas, the rate of cancer in Kota Baru, the rate of cancer in Machang. So by looking at the rate of cancer, then you can see which area that have high rates of cancer. So you know that might give you some hypothesis if you know there are areas high or at risk for cancer. Secondly, you want to separate patterns from the noise. For example, if you see distributions of dengue cases, the spatial distribution of dengue cases, right? So is it really the distribution or the clustering lah, for example, clustering of dengue infections in areas are real, or is that just because of some other noises or error in the measurement? Next, almost similar, is to identify disease cluster. Okay, you can take or geocode of patients with dengue, and then look on the map, do some spatial data analysis, and look for any clustering of dengue, okay, or maybe COVID. Cumanya be careful, because most of the time you will see or you get results with positive clustering, not because of disease to have clustering behavior, but because it's a functions of population density. For example kan, kita we see clusters of dengue in Kota Baru, in certain part of Kota Baru. We see certain clusters of dengue in Pasir Mas, certain part of Pasir Mas, not because that area are at risk for dengue, but because there are just more people there. Okay, there are more dense people in that area, and because of that, the number of dengue also increases. But if you divide the number of cases per population, actually the rate will always be similar. Okay, so be careful, don't take actual number, but take the number of cases, divide it by the population at risk. And you can also look for risk factors of certain exposure. For example, smoking, maybe vaccinations, and you can see the effect of smoking on the distributions of cancer cases, the effect of vaccination on the distributions of some infectious diseases. You can also do that. Okay, you can also do that. The last one, the assess significance of potential exposures, are basically analysis in the geostatistics, okay, or geostatistics analysis. Why we need a special analysis for spatial data? Spatial analysis for spatial data, okay, or a specific analysis for spatial data, because of the first law of geography. Okay, first law of geography, where Tobler in 1970 said that everything is related to everything else, but near things are more related to far things. It means that things that are closer actually more related than things that are further away. So if you go to, for example, to Desa Rahmat just dekat sana kan, dekat Demik tu, where there always high number of dengue cases, right? And why? Because people are living in dense area, and because of that, infections are more. Okay, so there is dependency, okay, or there is a dependency, kebergantungan antara cases tu, because they live near, and because of that, the risk of infections also gets higher, right? Gets higher. So this is different from the usual analysis that we have done before, for example, linear regression and logistic regression, when we say that the observations are independent. But now, if for example you do similar analysis, linear regression or logistic regression, but on data that that have some form of spatial relationship, for example dengue ke, then the assumptions of independence might be violated. Okay, and because of that, linear regression or logistic regression might not be accurate for your analysis. Right, we can discuss that later, right? So we need to have a special or specific analysis to handle this dependency. Okay, dependency or spatial dependency. We need to have specific analysis for that. We can do some form of linear regression, we can do some form of logistic regression, but that linear and logistic regression must take into consideration spatial dependency. Right. So that's basically analysis that you could do, and you might also want to visualize spatial data. Okay, so you can visualize point data. You can by looking at the points data, you can see the locations of the study subjects or patients or participants and by looking at these points you can see maybe spatial pattern. So you can see higher density of dengue cases in certain parts of Kota Baru, and you may see higher density of malaria cases in certain part of Kelantan, right? So you can visualize point data, and you can do a little bit more advanced analysis. For example, a kernel smoothing method to generate a continuous distributions of points data. So you can also do contour maps, image maps, so on and so forth. But more commonly people will do at least kernel smoothing method. This is one example of point pattern analysis where you see this is I think UK, and you can see points of drug. I'm not sure drug users I think maybe drug users, I think locations of drug users, and from this points you want to answer these questions. Is this pattern show, or does this pattern show some kind of clustering of drugs use, right? So that's maybe one question. Okay, ada clustering tak dalam drug use in this area? So that's why you want to know. So yes, number one, it can be evidence of clustering of drug use. So this is one example of a clustered data. This is random. It means that there is no clustering of drug use in this area because the pattern is random, and this one is regular. Okay, it means that yes, there is a pattern of drug use in this area and the pattern is regular. Okay, so there is clustered, there is regular, and there is random. Okay, this random. Okay. In addition to points data, you also have aggregated or area data. Okay, aggregated or area data. This involves summarizing a group of individual data points into a single value. For example, you can get the mean, median, or standard deviation. The most common form of data aggregation is, for example, counts of disease events. This happen if you consider for example a number of dengue cases lah. Okay, dengue cases, you instead you see the point, instead of you see the points, you don't have the points, you just have the number of cases, to 20, 78, 19, 2 to 41. So you don't have these dots, you have only an area, and then how many cases for that area. And how do we analyze this kind of data, or aggregated data? Tadi point data, now aggregated data. We can use choropleth maps or dot density map. Cumanya problems with this kind of data visualization for aggregated data is, number one, large study area dominate the display. For example, if you got Sabah, Sarawak kan, and if you imagine COVID-19 case kan dekat Sabah banyak kan, because Sabah is huge, you don't see Kelantan, Perlis, Melaka kan, you see, oh, Sabah, red. So because of that, you have that kind of where large study area will dominate the display. And then boundaries problem. For example, Sabah and Sarawak, right? Sabah has a lot of COVID-19 cases. Because of that, it becomes red. But Sarawak has very few COVID-19 cases and it becomes green. And then there is a boundary kan, antara Sabah and Sarawak. There is a boundary between Sabah and Sarawak. I mean, when you jump over the boundary, from red you go to green, from green you go to red kan. So it doesn't make sense, right? It doesn't make sense. You doesn't make sense. So you cannot just jump over a boundary and suddenly the area become low risk kan. There is no continuity and so there is a boundary problem. Yes, that's why if you set a limit like 40 cases per district to say it is red zone, I don't think it's a good number lah. Okay, you have to divide by the number of population in the area. Okay, because 40 cases in Selangor compared to 40 cases in Kelantan is very different, because Selangor is very dense area kan. So I think a better way to define red zone is to get the number of cases per population in that area. Okay, so right, okay. And also, is it difficult to visualize highly skewed distribution, because there is no continuity, just like Kelantan, Terengganu, Pahang, red, green, yellow, things like that kan. So it's difficult to visualize a skewed distribution. So this is an example of aggregated data and how you can use choropleth map to visualize aggregated data. So you can see kan, this area red and suddenly white or very light yellow kan, and then you have this sort of boundaries. So can you say that if you go one step in this area you are safe, and you go to one step to this area suddenly you became very very high risk? Maybe not so intelligent lah to say like that kan. But if you don't have data, points data, and you have only aggregated data, this is the best that you can do. This is the best you can do kan. So this is a choropleth maps that you can use to display aggregated data, and this is one example kan. And this is where this is United States of America kan. I mean, quite fair lah, because there is no area, there are not many areas that are very different in terms of dia punya size, right? Almost the same kan. Tapi kalau if you have a big area here kan, and other areas are small, then you can have that very distinct effect of that large area lah. Okay, so right, and then we have a continuous data. Continuous data, for example, rainfall, humidity, air pollution. Okay, these are considered continuous spatial data. Macam rainfall kan, dia tak ada boundary kan. So rainfall, humidity, temperature, air pollution, and this data usually comes from remote sensing organization lah. For example, macros kan, macros. So they will supply you with a map of rainfall for Malaysia, map of humidity for Malaysia, temperature for Malaysia, so on and so forth kan. So but still you can also plot using a choropleth map or also proportional maps. And last one which is quite advanced and not many people do this, is the geostatistics. Geostatistics sorry, geostatistics is where you have informations from that area. For example, if you want to study maybe immunity to COVID-19 lah. Okay, we take dengue lah. Okay, dengue. Okay, dengue. Let's say if we can measure the serology for dengue, the amount of antibody for dengue, right? If we can measure, right? If we can, I don't know, we can do it. No, if we can or we can't do that. But if we can measure the amount of antibody for dengue, then we can take that measurement from maybe 1,000 people in Kelantan. So maybe we take 200 from Kota Baru, 100 in Pasir Mas, maybe 60 in Tanah Merah, another 60 in Gua Musang, and then we draw blood, and then we measure the amount of antibody for dengue. Then we can make this kind of map. No, we can make this kind of map that will show you which area where people have higher level of antibody and which area where people have lower amount of antibody for dengue, for example. That's hypothetical. I'm not sure whether that can be done. This is quite advanced method. So you can do like inverse distance weighted radial based functions, kriging, co-kriging, INLA, integrated nested Laplace approximations methods, so on and so forth. But again, this is an advanced method of analyzing spatial data. So we have number one tadi, analysis of points pattern. Number two, we have analysis of aggregated data, and number three, we have analysis using geostatistics. Okay. So again, if you analyze data that have points, okay, dot, then you can look at area where you know what's this, a particular location is the where an event did occur. All right, okay. And then okay, I think what I want to say here is this is an extensions of the explanation lah. When I say that we can analyze points data kan, we can analyze point data, right? We can analyze point data. After that, what we do is we can check if the distribution kan, the taburan, the distribution of points to follow or does not follow complete spatial randomness. Okay, complete spatial randomness. It means that does it happen by random or does it happen not randomly? Okay, so kalau kita, so that's the hypothesis. Okay, so if you have points you can check for that. Okay, does it happen by random or does it happen by non-random? So if it is happen by random, then you say okay, actually there is, you know, this is happened by random. If you can show that it happens non-randomly, then you can say that there is a spatial process that affect the transmissions of the disease, for example. Okay, that's number one. You can also estimate the intensity, so you can count the number of points. For example, in Kota Baru, you can count the number of points or dengue cases in Kota Baru, Pasir Putih, Machang, Kuala Kerai, and then you can estimate the intensity. Okay, intensity. Right. So how to do that? How to check for complete spatial randomness? You can use what we call as homogeneous spatial Poisson point processes. Okay, homogeneous spatial Poisson point processes. Maybe you can read on your own this one. Okay, not that important, right? Next, spatial clustering. This is always an interest from epidemiologists, that we want to know if disease happen in clusters, right? So is there any spatial aggregation of disease event? So disease is considered clustered if there is residual spatial variation in risk after known influence have been accounted for. Okay. So you can look at the spatial point pattern for anyone, or you can do spatial point pattern for cases and also control. Okay, you take points from cases, you take points or location from control, and you see is there any difference or not between cases and control in terms of distributions of infections, for example. And then spatial regional count data, that is for aggregated data. And then clustering has a local and also has global clustering. Global clustering happens when the clustering is apparent or seems to happen throughout the study region. But local clustering, when cluster detection happen to certain locations only. Right. This is another way of doing the analysis, that is by measuring the spatial variation in risk. Okay, spatial variation in risk. How to do this? If you have the number of population for this area, then you got the points, and then for each area you can divide the number of cases per the number of population at risk, and because of that you can get the relative risk. So you can have relative risk for men and you can have relative risk for women. So if you divide between the two, you get what we call as relative risk ratio. Okay, relative risk ratio. So you can first of all you can see if there are areas that the risk of disease are higher. Okay, and number two, you can compare between men and women who are more at risk for spatial for specific diseases. Okay, so by again if you have points dot, and then you have the number of population, you can divide and the number of cases per the number of population, you get the relative risk. So you can get the relative risk for men, you can have the relative risk for women, and then you can even compare between men and women who is more at risk for the disease by dividing relative risk for men over relative risk for women. So you get relative risk ratio. All right. This is another example of geostatistics. geostatistics, where you can take you go to this area and then you take sample from throughout the region, maybe 100 here, maybe 200 here, maybe 300 here, maybe 400 here, and then you measure if each one of them has falciparum infection. Okay, so let's say you got 1000 subjects. Okay, you take 100 here, 300 here, 400, you got 300 here, you got 300 here, and then each one of them you take blood and you test for falciparum infections. Okay, so you get positive, negative, positive, 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 negative, positive, 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 negative, positive, negative, positive, 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 negative, things like that. And then from there you can make a map that will show you where are the areas high risk for falciparum infection and where are the areas that have lower risk for falciparum infections. Okay, so and you can and then you can also get other information. For example, from 1000 subject study too, you can take their age, take their gender, take information about whether they are using bait net or not. Okay, bait net or not, and you can do analysis to see if bait net coverage associate with lower risk of falciparum infections. Okay, so this is an example of a geostatistics analysis, right? So that is also an example of spatial exposure data analysis, where and you might ask me, kan, why can't we just do logistic regression, right? Why can't we just do logistic regression? Take 1000 subjects and then ask them and then check if they got infection or not, and then just run logistic regression. Cannot, because the usual logistic regression assumes that there is no spatial dependency, but from here it is obvious that there is spatial dependency. Respondents or subjects that are staying in this area have a lower risk of infections, whereas subjects that stay in this area have higher risk of infections. Because of that, the assumptions of independence has been violated, and you can't use the conventional logistic regression. You have to resort to geostatistics to have a more valid inference. All right, so I know this is a little bit complicated lah. I think a little bit complicated. Take some time to understand this, okay, and hopefully you can also spend time to read these two papers, Paul Elliott and Daniel Wartenberg. Paul Elliott is very influential in spatial epidemiology. So there is a very good paper, not too long, Spatial Epidemiology, Current Approaches and Future Challenges, which you can download from this link, and also another paper in Annals of Epidemiology, Advances in Spatial Epidemiology and Geographic Information System. Sorry. Okay, so this paper you must read, you must read these two papers. Okay, you must read these two papers if you want to learn more about spatial epidemiology and spatial data analysis. You can read these two books, Spatial Analysis in Epidemiology, very thin book, Spatial Analysis in Epidemiology, tak tebal pun, nipis je. And then Applied Spatial Statistics for Public Health Data. Okay, this is tebal sikit buku, Applied Spatial Statistics for Public Health Data, quite a thick book. textbook, but these readings are optional for you. Okay, so right, I think that's all. Any question?